Notice, this video solely focuses on grid north and true north. However, it is important to note that these are not the only north references that exist. Other north references include magnetic north, which points towards the magnetic pole of the Earth's northern hemisphere, astronomic north, which is determined directly through astronomic observations, and geodetic north, which is astronomic north corrected for the deflection of the vertical, to be the Laplace correction. While these references are not relevant for calculating grid azimuth, it is beneficial to be aware of them. As a professional land surveyor, or anybody using the North Carolina State Plane Coordinate System, it is important to know how to convert a true azimuth into a grid azimuth, or vice versa. An example of when this might be necessary would be when a professional land surveyor is hired to provide alignment of a transmission tower and the client requests the true and geodetic azimuths. Being able to provide such information is an important part of being a land surveyor. Before we look at the formulas for calculating true and grid azimuths, it's important to understand some basic terminology. A meridian is simply a north-south line from which differences of longitude are determined. Though it is a line, a meridian is not straight, as it follows the curve of the Earth from its poles. Meridians are also used to calculate something called azimuths. An azimuth is a horizontal angle measured clockwise between a point of interest and any reference meridian, which can be true north, grid north, or any of the other types of north references that were mentioned earlier. Although measurements of azimuths in the late 19th and early 20th century were frequently referenced from the south, professional surveyors today most commonly use north. Azimuth measurements are measured in degrees, ranging from 0 to 360. North translates to 0 or 360, east to 90, south to 180, and west to 270. Bearing is similar to azimuth in that it involves direction. Unlike azimuth, however, it is referenced from either north or south, taking into account the angle to the east or west from the north-south meridian. Additionally, bearing only ranges from 0 to 90 degrees. Azimuth and bearing can be converted back and forth to indicate the same direction. 241 degrees azimuth, for example, would be south 61 degrees west. 113 degrees azimuth would be south 67 degrees east. The formula to calculate grid azimuth is true azimuth minus theta, also known as a convergence or mapping angle, plus the second term, a correction for curvature. This means the formula for true azimuth is grid azimuth plus theta minus the second term. To understand how to utilize these formulas, it is imperative to understand what each of these terms mean and how to find them. Grid azimuths are calculated in reference to grid north, which is the direction of a grid line that is parallel to the central meridian of a grid projection. In other words, grid azimuths are not calculated from meridians, which follow the curve of the Earth, but from map projections that depict the curved Earth as a flat plane. True azimuths, on the other hand, are based on true north, which is the direction of the line of longitude that converges on the North Pole. Of note, longitudinal lines are in fact meridians, as they do follow the Earth's curve. Although there is only a very small difference between true north and grid north, one that can largely be ignored for navigation, this technicality is very important to take into account for land surveying, which requires much more specificity. This difference results from the impossibility of translating between a flat map and a round Earth. Also important to consider is that the difference is not always constant, rather changing dependent upon location. While there is no variance at all between the two north references along their shared central meridian, as you move towards either edge of the map, the difference between true north and grid north gets greater and greater. The formula also contains the symbol theta, which represents the mapping or convergence angle, or the angular difference between the true north and grid north. Calculating this requires some math, and also entirely depends upon the location where the survey is being done. In North Carolina, the ratio of theta to the longitudinal difference from the central meridian is 0.5717170255,241, which means 1 second of longitude is equal to that number of seconds. First, subtract the longitude at which you are conducting your survey from the longitude of the central meridian, which is 79 degrees. Second, multiply that by the theta ratio mentioned earlier to get your actual theta angle. Theta should be positive if you are east of the central meridian and negative if you are west of it. Again, it is imperative that the provided theta ratio is only used in North Carolina and nowhere else. This ratio will be different in other locations. The last part of the formula includes something known as the second term, which serves as a correction for curvature. It is a very minor adjustment and generally only needed in surveys spanning greater than about 10 miles, as this is when the curvature starts to have a notable impact. To calculate the second term, simply follow the following formula. The variables of this formula include x, which represents the east coordinates, y, which represents the north coordinates, and y0, which is a constant representing the northern coordinate of latitude 35 degrees, 15 minutes, 6 seconds, at the 79th degree meridian. Of note, y0 is relative to our location in North Carolina, and its value would be different elsewhere. With all of our variables accounted for, all it takes is some basic math to fill out the formula.